Hello students, welcome to EPG Pathshala Biophysics. I am Dr. Ravi Majumdar, Emeritus Professor, Department of Natural Sciences, West Bengal University of Technology in Kolkata, and formerly I was Professor and Head, Biophysics Division, Shah Institute of Nuclear Physics in Kolkata. Today we will talk about tunneling through potential barriers and proton tunneling in DNA. Name of the paper, as you all know, is Quantum Biophysics. Now, what are we going to learn from this lecture? Tunneling probability through potential barriers, then half-life for radioactive nucleus and alpha particle energy, then scanning tunneling microscope, which is called STM, and finally, proton tunneling and spontaneous mutation in DNA. In the last lecture, we have learned about potential wells. So in this lecture, from potential wells, we turn to potential barriers. Rectangular barriers are easier to handle. When a free particle hits such a barrier, there is a small but finite probability that it leaks through the barrier, even if it doesn't have enough energy to jump across the barrier classically. This is called tunneling, and it is important to find the tunneling probability for a rectangular barrier. Tunneling is a novel phenomenon in quantum mechanics. Remember that we came across a similar situation for a finite rectangular well where the trapped particle could be observed outside the classical domain. We discussed this in the last lecture. Now, the examples of tunneling through non-rectangular barriers are also considered with applications to alpha particle emission in radioactivity, which is a very important application of non-rectangular barriers. It's in fact called Coulomb barrier, as we shall see. Then the scanning tunneling microscope and spontaneous mutation in DNA as a result of proton tunneling across the hydrogen bond. This is a very important application of the concept of tunneling in biology.
Let us now tell you about the objectives of this lecture. Number one, a formula for tunneling probability of a particle through one-dimensional rectangular barrier is obtained in terms of the height and width of the barrier. Number two, extension to non-rectangular Coulomb barrier helps us to calculate the tunneling probability of alpha particles from radioactive nucleus and the half-life for radioactive decays. Number three, the principle of working of a scanning tunneling microscope, known as STM, is described as a practical application of the electron tunneling current involved. And finally, a spontaneous mutation of DNA can be due to the possibility of proton tunneling along the hydrogen bonds. So first, tunneling through rectangular potential barrier. So in the previous lecture, we have talked about the potential well. Now, this time we are talking about a rectangular barrier instead of a rectangular well. So you can see on the screen, you see how a barrier looks like. So we're considering a particle which is once again constrained to move in one dimension along the x-axis, and you have a one-dimensional potential barrier which is shown. So the length or width of the barrier is L, and the height of the barrier is V0. And now a particle is incident from the left on the barrier, and finally it passes through the barrier and comes out of it. So you can see the waves in all the three regions, 1, 2, and 3. Now a free electron or a nuclear particle, for example, an alpha particle, is incident from the left on a one-dimensional rectangular barrier of height V0 and width L. So assume that the particle doesn't have enough energy, E, to jump across the barrier because the energy of the particle is less than the height of the barrier V0. So classically, it cannot jump across the barrier, but quantum mechanically, it can cross the barrier because of its wave nature. So the Schrodinger equation is, as usual, d square psi dx square plus 2m by h cross square times c minus v psi equal to 0. So we consider the various regions. Now you have three regions. The first region is, you see, when there is no potential, that's before the particle or the alpha particle enters the barrier. The solution of Schrodinger equation is similar to that in the inside region of a potential well. The resulting periodic solution involving sine and cosine can be expressed in a more general form. That is, instead of writing sine and cosine solutions, we have changed it to the exponential form e to the power ikx and e to the power minus ikx. Well, the solution can be expressed in this form as well. And k, that is the wave number as before, is 2me under root upon h cross. The solution represents a plane wave where the first term is an incident part moving forward along plus x, and the second term is the reflected part moving backward along minus x. And then we come to region 2. In region 2, potential V is equal to V0, and we should remember that the energy of the particle is less than V0, so that it just it cannot cross the barrier classically. The equation is similar to that in the outside region of a finite potential well. The solution has the following exponential form, that is psi x is equal to e to the power alpha x plus d e to the power minus alpha x. So this the first one was periodic solution. Region 1 in the second region is the exponential solution, which is also reflected in the figure which you just saw. So in region 2, this includes the transmitted and the reflected parts of the wave, C and D. And then finally, the region 3, you have the potential equal to 0 again, so that the particle is a free particle when it comes out of the barrier. But this time the solution is again of the periodic type, psi x equal to f e to the power ikx. Well, it doesn't have a term containing minus ikx as in region 1, since there is only transmitted part in this region and there's no reflected part. So that's why there's only one constant f. How to go ahead with these equations? The functions psi x and its first derivative d psi dx must match at the two boundaries x equal to 0 and x equal to L, giving the following four boundary conditions. So you can calculate, d psi dx in each case, and you get the following. The boundary conditions gives you the following results, that is the a plus b equal to c plus d, and the next three. Okay, so these are the equations which you obtain from the boundary conditions. Now, since there are 5 constants, a, b, c, d, and f, we can determine the ratio of any two, because there are 4 conditions and 5 constants. So you can determine the ratio of any two. The most important ratio is the transmission coefficient or the tunneling probability across the barrier, which is T equal to F upon A square. And you see, we have the freedom of, setting A equal to 1 for the incident wave. Okay, that sets the scale for, the other constants. So we put A equal to 1, and so the transmission coefficient, or the tunneling probability, as we call it, across the barrier, is given by F square. So clearly this phenomenon is classically forbidden for a particle of energy E less than V0, but it's possible due to the wave nature of the particle, as I have already mentioned several times, because this is one of the most important points here. So it's easy but tedious to check. The transmission coefficient is equal to 4 alpha square minus k square square, then sine h square alpha L plus 4 alpha square k square divided by cosine h square alpha L, where you already know what are k and alpha from the solutions of the Schrodinger equation. Well, this calculation is very simple but tedious, because you have to do a lot of algebra to come to this equation for the tunneling probability, which is T. So we can make some simplifications. Assuming alpha L is very much greater than 1, which is usually the case for V0 very much greater than E. If we assume that, the height of the barrier, V0, is much larger than the energy of the particle, then we are justified in assuming that alpha L is very much larger than 1. And under this approximation, sine hyperbolic alpha L and cosine hyperbolic alpha L, assume simpler form. Transmission coefficient of the tunneling probability is given by a simpler formula, which you can see on the screen, that is 16 alpha square k square exponential e to the power twice alpha L divided by alpha square plus k square whole square. Now, if you use the expression for k and alpha, then you will end up with the following expression for the tunneling probability, which is TE equal to 16E V0 minus E upon V0 squared, then the exponential term, which is shown on the screen. Now, this is the formula for tunneling probability for a particle of energy E incident on a rectangular barrier of height V0 very much larger than E. The probability falls off exponentially with L and root m. That is, if you increase the width of the barrier L, then the probability will fall off very fast, and it will also fall off very fast if you sort of increase the value of m. Now, let us introducing the parameter epsilon equal to E by V0. The tunneling probability can be expressed in the form TE equal to 16 epsilon times 1 minus epsilon to e to the power minus 2 alpha L. So this is approximately 16 epsilon and exponential minus 2 alpha L. Since the probability is highly sensitive to barrier dimensions L and V0, the exponential terms plays a key role in fixing the tunneling rate. So an approximate expression is, you can see TE is equal to exponential of minus 2 alpha L, and you can put the value of alpha, then you can get what you see on the right hand side of this equation, of the first equation. So this can be generalized to any arbitrary shape of potential barrier Vx extending over a given range of x. Now, if Vx is larger than E in the range x between 0 and L, this will involve an integration over the classically forbidden region, leading to TE equal to exponential 2h divided by root 2m, then the integral, which you can see on the screen. The first of these formula applies to a rectangular potential barrier, and the second formula, which you can see on the screen, applies to a barrier which is of an arbitrary shape. An example of non-rectangular barrier in real life is the Coulomb barrier outside an atomic nucleus. Now, Coulomb barrier is very important in studying radioactivity, that is, the emission of alpha particles from a radioactive nuclei is a result of tunneling through a Coulomb barrier, and we are going to study this problem in some detail. So now, as I told you, we are talking about the emission of alpha particles in radioactivity. So you see the figure shows the nucleus, the particle is in the nucleus. Well, the circle at the bottom shows the nuclear radius, and the particles, that is the neutrons and protons, these are confined in the nucleus in a deep rectangular potential well. And you see the figure also shows alpha particles escaping from the nucleus. See, when it attains a certain energy level E, see, inside the nucleus, and when it is prepared to escape the barrier, well, it faces, when it prepares to escape the nucleus, it faces a Coulomb barrier. It has to sort of tunnel through the Coulomb barrier, and there is a tunneling probability which will decide the rate of emission of alpha particles from a radioactive nucleus. So the classically forbidden region is from R to R0, which is shown in the figure, where R0 is given by E equal to V as a function of R0. It is observed that the alpha particles within the radioactive nuclei are emitted spontaneously with kinetic energy ranging from 4 to 9 MeV, that's million electron volts. And then half-life of parent nucleus is found to be highly sensitive to this energy and varies from a fraction of a second to million of years. So this is very important to note, that you see the emitted alpha particle energy varies from 4 to 9 MeV. But you see the corresponding half-life of the radioactive nuclei varies from fraction of a second to millions of years. Now our aim is to see how the classically forbidden emission takes place as a result of tunneling through a non-rectangular Coulomb barrier and accounts for the widely varying half-lives. So inside a parent radioactive nucleus, an alpha particle can be seen in a deep nuclear potential well, as I said, of radius r equal to of the order of 10 to the power 14 meters, which is about 10 Fermi. Well, that's approximately the size of a heavy nucleus, you see, from which alpha particles are emitted. Now, as the alpha particle consists of 2 protons and 2 neutrons, so the atomic number is 2. So as the alpha particle acquires energy E and prepares to escape from the nucleus, it faces a long-range Coulomb barrier. Well, you can find that this barrier, Vr, is equal to 2k Ze square by r, operating outside the nucleus. This is because of its electrostatic repulsion of the daughter nucleus, well, the atomic number is Z, in the immediate vicinity of the nucleus, where the Coulomb barrier Vr greater than E can be as high as 30 MeV and falls below E only at R equal to R0. So this is a very important point, that the escaping alpha particle, faces a non-rectangular Coulomb barrier as soon as it comes out of the nucleus, and it has to tunnel through this barrier, for which we want to find out what is the tunneling probability. That will give us the rate of alpha particle emission and also the half-life of the radioactive nucleus concerned. The next point, for example, in the case of radium, an alpha particle with energy E equal to 4.9 MeV is unable to cross the barrier and the emission is classically forbidden. In real life, the alpha particle can still escape through an alternative route of quantum mechanical tunneling. So this is a very important point. Though the probability of tunneling is enhanced by repeated collisions of the alpha particle against nuclear wall, well, it is estimated that the frequency of such collisions is 10 to the power 21 per second. That means billions of collisions it suffers within the nucleus per second. So, this enhances the probability of tunneling. But in spite of this, the probability is still very small and can be estimated by using the formula for tunneling probability for non-rectangular barriers. Now, in spite of a small probability, you see the presence of a huge number of atomic nucleus in a radioactive sample is found to maintain a steady emission of alpha particle. The probability of tunneling is very small, but in spite of that, well, in real life, we find that a steady emission of alpha particle is maintained by a radioactive source. Now, why is it so? Because you see there is a very large number of atoms present in the radioactive source, and this number is of the order of Avogadro number, which is 6 into 10 to the power 23 per mole. Okay, so you have billions of atoms which are present in the sample, and so in spite of the small tunneling probability, you can find that you see a steady emission of alpha particle is maintained by the radioactive samples. So let's come to the tunneling probability and nuclear half-life. Referring to Coulomb barrier, the forbidden region is from to capital R0 you see, referring to the figure which you already saw, so that the integral under the formula for tunneling probability for non-rectangular barrier is expressed in terms of the variable r as the integral which is shown in the figure. That's the integral from r to r0, and the integrand is VR minus C root. So this is integrated with respect to r. So this integral is involved. And so our main aim is to manipulate this integral or in such a way that we can find its value. So that's exactly what has been done. So here r is the nuclear radius, capital R, and Z is the atomic number of the daughter nucleus, as we already mentioned, and E as a function of VR0 is the energy of the escaping alpha particle, which gives R0 equal to 2k Ze squared by E, as it was marked in the figure which you already saw. So you see, an approximation evaluation of the integral leads to the tunneling probability, which is T exponential of, you can see minus 4 pi Z root of E0 minus E, and then plus 8, then root of Z times capital R divided by R0, where the parameter R0 is, and the parameter E, these are the two parameters which are entering here. So the values of these parameters can be estimated. So R0 is 7.25 Fermi, and E0 is estimated to be about 0.1 million electron volts. So actually we didn't devote much time in evaluating this integral because this is a mathematical problem. So we are only concerned with the result for the tunneling probability, so which is given by dE, and the constants and the parameters R0 and E0 are taken to be known parameters. Since the decay probability is enhanced by repeated collisions of alpha particle against nuclear wall, which has an estimated frequency of 10 to the power 21 per second, or 10 to the power 15 megahertz, the probability of alpha emission per second, or the decay rate lambda, you see, becomes lambda is equal to f, that's the frequency, which is 10 to the power 15 megahertz, f times TE. And so that turns out to be 10 to the power 21 times, you see, the tunneling probability, which is written here. So the result can be expressed as the familiar Geiger-Nettel law, that is log lambda equal to minus A1 Z upon root E plus A2, where A1 and A2, these are constants, you see, which can be determined, you see, but I'm not going into the details of these constants. Well, it can be determined by doing some algebra. The half-life of radioactive element is given by, you see, the half-life is denoted by T half. So that is equal to the natural logarithm of 2 divided by lambda, and which is 0.693 divided by lambda, where lambda is given by the formula which involves, you see, the natural logarithm of lambda. That's the Geiger-Nettel law. Now this helps us to estimate the decay rate or the half-life of a radioactive element by measuring the energy of the ejected alpha particles. So what you do is that you measure the energy of the ejected alpha particle, which is E. So you measure this energy, which if you measure, you can get from this formula, you can get lambda, and by using this value of lambda, you can find out the half-life. Okay, so that was the main problem. You see, how can we find out estimate the half-life of the radioactive nucleus by measuring the energy of the ejected alpha particle? So that's how this is done. And finally, we would like to mention that the half-life of a radioactive element is highly sensitive to the energy of the ejected alpha particles. As I mentioned it before also, it can vary from a small fraction of a second to millions of years. So let us take a few examples now. Let's take the example of the radioactive element thorium. We consider two extreme cases. One is the radioactive thorium, which has a half-life of billions of years, and secondly, the radioactive element polonium, which has a half-life which is less than billionth of a second. So the observed energy, I'm considering the first one, the observed energy of an ejected alpha particle from the radioactive element thorium, the nuclear size is about 9 Fermi, is 4.05 MeV. Now, using tunneling model, the half-life for decay of thorium into the daughter nucleus is found to be 0.693 divided by lambda, and lambda is calculated from the Geiger-Nettel formula, by using the energy equal to 4.05 MeV. And if you calculate the half-life, it turns out to be 1.7 times 10 to the power 10 years, which is more than billion years. So this is what happens in the case of thorium. In the case of radioactive element polonium, having the same nuclear size, the daughter nucleus is lead, and the observed energy of an ejected alpha particle is found to be 8.95 MeV, so which is about twice the value for thorium. You see, for thorium, it is 4 MeV, and here the energy is about 9 MeV. So it's the energy of ejection is about twice in this case. But if you calculate the tunneling probability, estimate, lambda by using the Geiger-Nettel formula, and then finally calculate the half-life, it turns out to be 8.4 times 10 to the power minus 10 second. So this is less than billionth of a second. So I took these two extreme examples just to note that, the difference in the ejected energy is just twice in the two cases, but the half-life varies from billion years to the billionth part of a second.
I repeat that the half-life of a radioactive element is highly sensitive to the energy of the ejected alpha particle. This can be best demonstrated by comparing the energy of alpha emission and the corresponding half-life for the elements thorium and polonium. These are the two extreme examples. In the radioactive element thorium, alpha particles are emitted with energy of about 4 million electron volts, which is written as 4 MeV, and its half-life is about 1 billion years. Mind you, it's 1 billion years. Whereas in the radioactive element polonium, alpha particles are emitted with energy of about 9 MeV, which is only a little more than twice the energy of alpha particles in thorium. But in this case, the half-life is about 1 billionth of a second. Mind you again, it's 1 billionth of a second. So these results can be checked from the tunneling theory as shown in the examples appearing on the screen.
This is a practical application of quantum mechanical tunneling. This is based on tunneling current. The diagram, you can see in the diagram, the STM can detect even atom scale variations on the surface of a metal or semiconductor. Well, if you have a plane, like the top of a table might appear to you as plane, but it may have atom scale variations. So the tunneling microscope, this STM can detect, such small variations on the surface of a metal or a semiconductor. Then as the tip of a conducting tungsten needle is brought close to the surface, as you can see, it's in the figure, there is a tip, and this tip consists of a conducting tungsten needle, and if this is brought close to the surface, an applied voltage causes free electrons to tunnel through the gap between the tip and the surface of the metal. Where they encounter a Coulomb barrier, it can be shown that it encounters a Coulomb barrier similar to the one which is faced by alpha particle. And the probability of tunneling of the electron across this gap shows up as a tunneling current. The tunneling probability is highly sensitive to the sites of the intervening gap where it encounters a Coulomb barrier. So even an atom scale variation in the gap causes the tunneling current to vary and become detectable. As the needle scans across the entire uneven metallic or semiconducting surface, the resulting variations in the tunneling current are amplified and translated into an image. STM has been used successfully to obtain the image of a double helical DNA molecule placed on a suitable surface where the width of this chain molecule is about 2 nanometer. So by using the microscope, you can even sort of see a DNA, not in full details, but you can detect the presence of DNA on a surface. You can directly observe it through this kind of microscope, which is based on tunneling of electrons. And then finally, I would like to mention that STM, the scanning tunneling microscope, is the precursor of an even more advanced and recently developed atomic force microscopy. Well, this is a very important technique for determining the surface properties of substances, that is the atomic force microscopy. Finally, we talk about spontaneous mutation in DNA, well, which could be a result of proton tunneling through a potential barrier along the hydrogen bonds in a DNA molecule. So you can see in the diagram the asymmetric double well potential along hydrogen bond in DNA. So the potential well, you see, consists of a deeper well. The potential consists of a deeper well, you see, and a shallower well. Normally, the proton exists in the deeper well. So let me just read out what is given in the what you can see in the screen. Base pairs of DNA double helix are coupled by a series of weak hydrogen bonds between them. An asymmetric double well potential exists along a hydrogen bond, and these wells are separated by a potential energy barrier, as shown in the figure. The proton involved in a hydrogen bond normally rests in the deeper well, but in real life, there is a very small probability that the proton may tunnel through the barrier and occupy the shallower well, which is again shown in the figure. If the DNA replicates by any chance when the proton is in the shallower well, then the usual base pairing rule for the DNA double helix may be temporarily jeopardized. If this happens, the mismatch of replicating base pairs may lead to errors in the genetic code causing mutations. These are called spontaneous mutations, as there are no external or environmental agents involved in the process. So now it is believed that spontaneous mutations can be responsible for aging and cancer. In principle, the rate of these mutations can be related to the proton tunneling probability. Since the probability is highly sensitive to the shape of the non-rectangular barrier involved, it is extremely difficult to relate this to the mutation rate. Well, several scientists have tried this. Well, we also tried, but see, we couldn't sort of connect the mutation rate satisfactorily to the tunneling probability. But one thing is more or less clear, that the spontaneous mutation is due to proton tunneling, which is an application of the tunneling probability of particle across potential barriers.
Let us now summarize what we have learned from this lecture. The expression for tunneling probability of a particle through one-dimensional rectangular barrier suggests that it is highly sensitive to the height and width of the barrier. The tunneling probability of alpha particles from radioactive nucleus is calculated on the basis of a non-rectangular Coulomb barrier. This leads to Geiger-Nettel law. This is a famous law. Results indicate that half-life for radioactive decays varies from small fractions of a second to billions of years. So this has been illustrated in this lecture. Now, in scanning tunneling microscope, which is usually called STM, the electron tunneling current is utilized to detect even atom scale variations on the level of conducting surface. It's a precursor to more recent atomic force microscopy. The mutation of DNA, often leading to cancer, results from genetic errors. These errors are caused not only by environmental factors, but also by the possibility of proton tunneling along the hydrogen bonds in DNA. Well, these are known as spontaneous mutations.